Hello and good day everyone, my name is Ron and let us answer some neural networking problems. Create an artificial neural network using MATLAB for the dataset provided for the DWSIM neural network demonstration. The file is available in our Blackboard course homepage. Determine what is the R-squared value and the MSE. Try varying the hidden layers in the ANN model. What did you observe and display the regression plot? So this is the data that corresponds to the question seen earlier. So this is a data regarding heat exchanger data where the W refers to the mass flow rate, the temperature, the T is for the temperature, and the HX is the efficiency of the heat exchanger. So the first thing to do is to identify which of these are the inputs and which of these are the outputs. It might be confusing given the variables alone, but all we need to do is just create our own diagram of a typical heat exchanger. So this is my attempt of a crude heat exchanger diagram, and as you can see here, there is a cold inlet going in and a hot inlet going in, and after it exchanges heat, it exits as the cold inlet exits as a warm outlet and the hot exits as a cool outlet. So this means that the WH or W hot corresponds to the mass flow rate going in for the hot liquid, and for the W cold is the cold liquid. And then afterwards, the T in cold is of course the temperature of the inlet of the cold and the temperature of the outlet of the cold. T in cold, T out cold, and T in hot, temperature inlet of the hot fluid and temperature outlet of the hot fluid. So HXF EFF is simply the heat exchanger efficiency. Now, what are the inputs? Well, by this diagram, it's easy to identify that the inputs are the W hot, the T in hot, the W cold, and the T in cold. We have 4 inputs. And then what's the overall outputs? The outputs are T out cold, T out hot, and the HXEFF. So essentially, these 4 are our inputs, and these last 3 are our outputs. Okay, so now since we identified the inputs and outputs, it is time to create our artificial neural network. First, go to MATLAB, and next we need to create a Excel data here in MATLAB. So click New in the workspace and click here Input. Then we need to have another Excel workspace. We will put here Output. Alright, double click on the input and we will be given in this interface. Now we need to highlight all the input variables, all data corresponding to the input variables. Click Copy or Control C, then Paste. Then as it pastes, right click and transpose variables so that it will be in a horizontal orientation. So that's the input. And as you can see, the input is 4 times 500 and 4 and 500. Then for the output, double click, then highlight, same, but for the output variables, Control C, copy paste here, and then transpose the variable. So 3 times 500, then input 5 times 500. Alright, looks like our inputs and outputs are ready. Now it's time for the artificial neural networking. So go to Apps, and if you haven't downloaded the machine learning deep learning, please download the package. It's free to download in the MATLAB store. Then after downloading the machine learning deep learning, we need to click on neural net fitting. This is the application we will use, and this is the interface. You click Next. Our inputs is already defined. Click here Input 4 times 500. Our input is also 4 times 500 here. Then for the outputs, 3 times 500. Okay. Matrix columns, next. And here is the percentages. We'll just leave it as is. And click Next. Afterwards, this is where the hidden layers or hidden neurons come into play. So I created a table here in the same Excel, but that allows us to summarize everything that we know. So let's start first with 2 hidden neurons. Then we increase the hidden neurons up to 20. So first things first, let's just put here for 2 hidden neurons. Click Next. Then we'll pick the training algorithm, Levenberg-Marquardt. And afterwards, we click Train. So the training is done, and these are the data or datum. Now, how do we find the MSE or R or the plot? So just click here, Plot Regression. And here we are. So this is the regression plots of the respective of the ANN or the artificial neural network at 2 hidden neurons. And according to according to here, the regression plot states that the training R value is 0.9986. So we go here, 2 hidden neurons, training R value 0.9986, and then for the validation it is 0.99826, and then for the test 0.99891, and then for all is 0.9986. 0.99861. Okay. Afterwards, we need to find the R-squared data of this, so the R-squared variable. So we just click here, this one, and square it. Then we have the following R-squared variable, the R-squared values. Then we need to find the mean squared error. The mean squared error is simply, you can find it not in the following graph, but in this graph. Sorry, in this section here. The MSE is 59.5732. 59.5732. So for training, 59.5732. For the validation, 17.5949. And the testing is 47.4740. 47.4740. Alright. And there's nothing for all, so we'll just leave this as blank. So afterwards, this is the value results that corresponds to 2 hidden neurons. Alright. However, we need to do it up to 20 hidden neurons, so this might take time, but so I will just cut this video and forward you to the final output of this Excel. However, take note everyone that training multiple times will generate different results due to different initial conditions and sampling. So in short, the ANN is probabilistic in nature. We cannot exactly have the same result for every run that we do. However, we can observe a pattern by repeating the results again and again. But in this case, for this video, I would only do the run one time, record it, and change the hidden neuron again, run one more time, so on and so forth, until I can fill up this Excel table. So, with that in mind, after filling everything up from the patterns of hidden neurons from 2 to 20 as said earlier, here are the following MSE, R, and R squared data, for the different training, validation, testing, but for MSE it doesn't have the all, so we just need to put it black. But for R and R squared, the R, again, as I said earlier, I just inputted from what is given in the simulator, or the MATLAB value, then the R squared, I just squared the value of the R. So this is the compilation of all results given here. This is when the latest hidden neuron is in 20 hidden neurons. This is the regression plot. Now, in order to observe the patterns, this is the mean squared error. So I graphed it using a line graph where the x-axis represents the hidden neurons and the y-axis represents the values of the MSE and the R squared respectively. I did not try to find a line graph again for R, since essentially they're just the same pattern, R and R squared, since it's just the square value of R. I only opted to plot the MSE and the R squared value respectively, since that is what is being required in the problem given. So the mean squared error patterns are as follows. So as you can see here, this is in respect to 2 to 20 hidden neurons. So in the training, it decreases as hidden neurons get higher, but it increases a bit. There's like an optimal point where the MSE value is at the very least. Same here for the testing, which is the gray line. It increased and decreased. It's like a roller coaster, but it has the most minimum point, which is in this part. Same thing for the validation. So it's like a roller coaster again. However, the minimum point is where the hidden neuron is 12. And now, according to statistics, there is no actual great value for the mean squared error, such that it's just simply a comparison between which model is better. So among the different types of hidden neurons from 2 to 20, I can conclude that at 12, since this is at the 12 data point, 12 hidden neurons, 12 and 12, at 12 data points, at 12 hidden neurons, the most optimal hidden neuron is 12, since it yields a mean squared error that's the least, or the least mean squared error value compared to the other hidden neuron variations. Now, in terms of the R squared value, it's the opposite. Since the mean squared error, the best is when it gets closer to 0, the R squared is the best is when it gets closer to 1. So as you can see here, the limit is from 0 to 1, and the pattern is similar to what we have in the mean squared error, such that in the training, it increases. No, more like the opposite. But the similar is that at point 12 is where the optimum or the maximum point where it almost reaches 1 yields. So at the training part, it increases, then decreases again, then it decreases a bit. So like a roller coaster again from the from the first graph. For the validation, same thing for the orange line. For the testing line, it starts from high, then low, high and low. So it's the gray line, and then the all line is similar to the training line. And the points at which that it receives the most the maximum value of R squared, or the value that almost reaches 1, is at hidden neuron 12. And it also corresponds again to the conclusion that hidden neuron 12, the number of hidden neurons, or 12 hidden neurons, is for the mean squared error. And the pattern, and the overall pattern, or the conclusion I can get, is that as hidden neurons increase in amount, the more that the model gains a more validated and tested neural network. But there will come a point when too much hidden neurons would lessen the efficiency of the network. That's why it's not simply a straight line, but more of a parabola, where we need to find the optimum or optimal hidden neurons in order to gain the most efficient model to represent our given data, network data. In this case, the network data is the heat exchanger data obtained from the DWSIM neural regression example. So, in conclusion, the optimum number of hidden neurons to truly describe our data is when there are 12 hidden neurons. This is of course, with respect to the points where there is 15% validation, 50% testing, and 70% training. And I can also conclude that since almost all, regardless of the number of hidden neurons, since almost all R squared values are approximately equal to 1, all values, or the XL data, which is the heat exchanger data, can truly be modeled using the artificial neural network in MATLAB. So again, my name is Ron. Thank you all for listening, and I'll talk to you all later.